Good day everyone. Today I want to present about Fluid Mechanics 2 assignment. My group consists of 4 members, me, Ganesh Kiran as leader, Levina, Teozichan and Vimalan. I am responsible to introduction, objective theory, video editing. Levina explain problem solving, geometry and dimension. Teozichan method simulation, explain result. Vimalan relates result with above theory and discussion. The topic given is laminar parallel flow over flat plate. The objective to analyze the velocity and the boundary layer development in laminar flow over flat plate using software. Evaluate the effect of different airflow velocity on the profile of the boundary form. Verify and validate theoretical prediction of laminar flow behavior over a flat plate using CFD simulation. The theoretical laminar flow is characterized by the smooth and orderly movement of the fluid particles along a parallel layer or streamline with a little or no mixing between adjacent layer. In fluid mechanics, one of the most widely studied cases of the laminar flow involving flow of the fluid over a flat plate. This type of flow finds application in various fields, including the studies of flat plate in heat exchange, aerodynamics, and etc. How to identify laminar flow? Laminar flow are smooth and streamlined, where turbulent flow are irregular and chaotic. A low Reynolds number indicates laminar flow, while the high Reynolds number indicates turbulent flow. The flow behavior drastically changes if it is laminar or turbulent. Reynolds number laminar is 10 power of 5, and we got two equations and the details. Thank you.
So for explain the problem that needs to be solved in the simulation, which is the objective. So the objective is to find the flow over a flat plate when the airflow is changed. In this case, it is 1 or 2 meter per second. So for geometry, we will edit the geometry in the design modeler, which is in ANSYS. So for geometry, we should click the geometry button to enter the design modeler. So for we are going to edit in 2D, so the grid should be in a 2D shape. So the major grid would be 0.1 meter and the minor steps per major will be 10. So for dimensions for group G, the V1 would be 1.5 meter and the H2 would be 0.3 meters. So for H2, which is 0.3, it is drawn as horizontal, which is H2. So for vertical, we take the V1, which is 1.5 meters. So to draw this surface, we should select the rectangle option in the draw toolboxes. So to set the V1 and the H2 in our drawing, we should select the general option in the toolbox to set our V1, which is 1.5, and our H2, which is 0.3 meters. So next we select concept, and then we select the our sketch, which is sketch 1, and then select surfaces from sketches. After that, after we click the surfaces from sketches, we should apply on the base object. Click on apply on base object, and then we click generate, and then we have our surface generated.
First, we highlighted the mesh from outline. We apply method sizing and face meshing from insert. From face meshing, the plane in XY direction is highlighted by blue color, which implies face meshing. At the same time, we check the detail box, making sure it is in the correct condition. When we highlighted edge sizing, the edge is acting on the top of the model. We use number of division with 50 and no bus for bus type in detail box. When we highlighted edge sizing 2, the edge sizing is acting on the left side of the model. 60 number of division and no selection of reverse bus is used. When we highlighted edge sizing 3, the edge sizing is acting on the right side of model. 60 number division and 1 edge for reverse bus is used. When we highlighted the airflow from name selections, the airflow implies the red color contour is full on the model. Then, our inlet is acting from the left side of the model, whereas outlet is the right side of the model. Besides, the plate is acting from the bottom, whereas far field pressure is acting from top side of model. And last, we generate the mesh. And now, we go to the workbench and highlighted the setup and edit. So we get a result from that. Now, we check from general. From model, making sure laminar is used in the viscous part. From material, make sure density is 1 kg per meter cube and 0.0001 of viscosity is applied. Make sure type fluid is chosen from airflow from cell zone condition. Then we highlighted the boundary condition. From inlet part, 2 meter per second of velocity magnitude is applied. From outlet, make sure pressure outlet is used and velocity inlet is used from inlet. And plate set to the wall type and far field pressure is set to the symmetric type. From metal part scheme, simple is used. This square cell base is used in gradient. Second order is used in pressure and second order upwind is used in momentum. Highlighted control. 0.3 is used in pressure, 1 is used in density, 1 is used in body force, and 0.7 is used in momentum. And we check the report definitions. Highlighted the initialization. 0 Pascal gauge pressure is used, 2 meter per second is used in x velocity, 0 meter per second is used in y velocity. Make sure standard initialization is used in the initialization method. At initial value, 0 Pascal is used in gauge pressure, 2 meter per second is used in x velocity, 0 meter per second is used in y velocity, and finally click initialize button. And now we highlighted run calculations and we get 1000000 in number of iterations. Highlighted the residual from monitor. 1e minus 0.6 is shown in continuity, x velocity and y velocity. So we click calculation from run calculation. We shift the mass to scale residual. Graph is shown. Black line of graph implies continuity, red line implies x velocity, and green line implies y velocity. From console, 1,4x solution is converged at the last part. So we edit the result. From CFD post, we get a majority orange color of contour color that implies 1.988e ++00, and a small rainbow exists at bottom of contour color. We change the direction of view. We off the contour 1. The graph exists like hollow. Observe from front view of model. Contour color 2 is used. We are on back the contour 1. All domain is used in domain. Symmetry 2 is used in location. Velocity is used in variable. 50 is used in contour and apply is click. We adjust the view of models and to observe the distribution of contour color. After that, we click from location and insert line is chosen by name line 2. Line 1
I will be presenting on the topic of boundary layer velocity profile. This presentation will cover the analysis of velocity profiles and boundary layer thickness for air flow over a flat plate, along with a comparison between simulation result and theoretical prediction. Let's start with understanding the velocity profiles within the boundary layer. At the wall, the velocity is 0 due to the non-slip condition. As we move away from the wall, the velocity increases smoothly, reaching a maximum at the center of the flow. In laminar flow, the velocity distribution is a parabolic in nature, as shown here. Here we see the velocity profile for airflow at the lower velocity of 1 meter per second. The velocity increases gradually across the boundary layer. This image illustrates the velocity profile at 1 meter per second. In contrast, here is the velocity profile for air flowing at a higher velocity of 2 meters per second. The velocity gradient within the boundary layer is much steeper. There is a rapid increase in the velocity from the surface to the free stream. This image shows the velocity profile at 2 meters per second. Now, let's compare our simulation results with theoretical prediction. Our simulation results match the trend predicted by the Wondershare solutions. The Wondershare solution provide a prediction for boundary layer thickness that we can use for comparison. We observe consistent trends between our simulation results and the theoretical predictions, validating our simulation model. Now let's discuss the effect of different airflow velocities on the boundary layer. For the velocity profile, lower velocities result in a gentler gradient and slower boundary layer. In contrast, higher velocity lead to a steeper gradient and a faster boundary layer. Regarding boundary layer thickness, higher velocity causes stronger initial forces, resulting in reduced thickness and greater mixing. Conversely, lower velocities result in weaker initial forces, a thicker boundary layer and less mixing. In conclusion, Our simulation successfully captures the characteristic of the lamina boundary layer. The consistency between our simulation results and theoretical predictions validates the accuracy of our simulation model.